Hey there, welcome. Today we are starting our journey through force and chapters 4 and 5. And so this particular one will kind of be introducing chapter 4, kind of what is a force, what are some different examples of forces. You can kind of see on the screen there some of the different topics that we'll be going through in this particular video. So it starts off chapter 4 and 5, we kind of combine them together. Chapter 4, we begin the concept of what force is. Start doing some math, with math with force and drawing some diagrams. You can see we've got force diagrams coming up. And then in chapter 5, we start applying forces to two different directions. So when forces are meeting at like right angles as opposed to all in a straight line. So we're kind of building upon some different ideas here as we combine these two chapters together. So like I said, we're going to start off with taking a look at some definitions of what forces are, and then we'll move into how do we represent them, some different types of forces, and then how do we draw them, basically some simple things like that. So first of all, may the force be with you and all that kind of good stuff. The easy definition of what a force is, it's actually really simple. If you think about it, it's just a push or a pull. That's really it. Anything that you can think of that you would call a force of some sort is either a push or it's a pull. You're either forcing something to go away from you or you're forcing something to come towards you. Push or a pull. Really easy definition to identify what a force is. But what does that mean when you apply a force to something? So forces typically cause things to either change their motion, or potentially we could say that balanced forces cause things to maintain their motion or maintain their position someplace. So typically when we're talking about forces and you apply a force to something, you're going to cause it to change what it's doing somehow, cause it to move away from you, cause it to move forward towards you, something along those lines. And anytime something changes its motion, it's accelerating. So always there is a tight relationship between forces and acceleration. If you apply a force to something and you change how it's moving, speed it up, slow it down, or change what direction it's going, by definition, you have to be accelerating that object. Only when you've got balanced forces in place where you're maintaining something's motion can we say that there's some sort of a connection between balanced forces and maybe say constant velocity or even holding still if that velocity is equal to zero. So like I said, force and acceleration are tightly interlinked in terms of concept with one another. So there's two general types of forces when we start talking about kind of what is a force, pushes and pulls and all that kind of stuff. And I'm not saying that the two general types are a push or a pull. That's not what I'm referring to at all. In fact, when we talk about the two general types of forces, the two categories are what we would call contact forces and field forces. Those are the two main categories. Now I'll go through a bunch of examples on the next slide. But in terms of defining what a contact force is or what a field force is, let me get my pen up here while I'm thinking about it. It's actually a relatively simple definition. Let me get my pen. There it is. Pen. That's what I'm looking for. So contact force, super easy. If I slap you in the face, I have applied a contact force. Contact force, when we're talking about these guys, require contact. Must contact. There is some sort of, at least at the macroscopic level, some sort of physical connection between those two things in order to have a contact force. So if you're literally think of a typical push or a typical pull, those are things that have to physically come into contact with one another. This is in sort of opposition to what we would call the generic case, which is field forces. And these guys are a little bit different over space. These are the types of forces where you don't necessarily have to have things touching one another in order for them to exert a force upon one another. Think magnets, right? Magnets can exert a force on something. They can cause something to be either attracted to it or pushed away from it. And they don't have to be touching each other. That's a field force. So contact forces require contact. Field forces exert some sort of push or pull over this sort of nebulous concept of a field. There's a space around that particular object through which they can exert their influence, so to speak. Contact, you got to be touching it. So let's take a look at some examples of this. This is sort of a sorting idea. It's meant to be sort of simple, but I'm going to put up on here some examples of contact forces, field forces, so that you can kind of have an idea in terms of sorting with there. And then each one of them has got a little picture that goes along with it. On the right, I'll kind of use some abbreviation letters so you can kind of see what we typically do. When we're abbreviating the letter force, by the way, force, its variable is always a capital F. Different types of forces, a lot of times we'll use a subscript of some sort, like f of x or something like that. Not f of x, I'm not talking about the math sense, but like f with a little sub x next to it. So typically when we're talking about types of forces, if we're just talking about force in general, you can use a big capital F. If you're talking about specific types of forces, we'll use a subscript letter to identify which type it is. So our first little picture is a spring. If you want to talk about spring force, spring forces are interesting. You can either talk about something compressing a spring or something pulling a spring, a compression or a tension kind of force. But either one of those, you have to have contact with the spring, right? It's not a field force. So spring forces like this, what have I just done? Spring forces like this are what we consider to be contact forces. So let me move this over to the side here. Wait, I'm gonna have to switch my tool here. Hold on. Sorry, epic technology fail here. That's the one I want if I gotta get that out of the way. So if I'm talking about my friend the spring here, spring forces tend to be contact forces, right? And if I wanted to abbreviate that somehow, I would typically use the letters like FSP, like F. Oops, what am I doing? I'm highlighting now. I'm a mess. Bedwell. There we go. F, something like this, FSP, something like that would be a spring force. It can either be like I said, a compression or a tension force. So next one, this one right here, dude pushing a car. Right? Typical kind of a push like we're thinking about. Obviously, you can't do that with your mind. Even if you think about it, it'd be lovely if we did. But that's not really how that particular process works. Don't you wish it was? So in this case, when we're talking about that kind of force, that's also a contact force. This kind of a force like this, when we're talking about this style, is usually applied FA. It's called an applied force, is a very common way that we would talk about someone, like I said, pushing a car, something along those lines. That's an applied force, FA. Move that over to the side. So there we go. Applied force. And again, FA, something along, oh, really? Why am I doing that again? Something like this, FA would be an applied force. All right, moving on to some of our other examples on here. With this one, we've got this gal that's picking up this large, heavy object. So what I'm referring to with this particular one is not just the applied force. She's got an applied force, right? It's her on the actual like barbell, right? Is an applied force. She's pulling it up. But what is she pulling up against? Right? So she is pulling up against the weight of the object itself. So the weight of the object itself, believe it or not, is indeed a force. Now, this is a different one, and this is kind of odd for what this is. So I'm going to be a little bit careful where I write this one. Let me get my correct pen going on here. Why does it keep changing? Okay, so put my correct pen up here. The weight of the object, what's creating that? Well, weight is due to the force of gravity. And this is the one I wanted to put over here specifically, Fg. Okay, Fg is weight. Weight, the weight of an object, not the mass of it. So the weight of an object is due to the mass, the matter that's in there, being acted upon by Earth's gravity. So I know it sounds funny, but she's got an applied force that's pulling up, but the downward force is actually Fg, or weight of that particular object. So again, I wanted to mention that one. So weight is a typical, and that's actually a field force. Again, you don't have to be touching the Earth in order to, otherwise you'd never be able to drop something, right? You couldn't be able to get off the Earth, you'd lose gravity as soon as you jump. All right, this one right here, dude pushing heavy object across floor. So he's working against the object's weight, of course, which is Fg. But when he's pushing it, right, you know that there's different surfaces you could push it on. You could push it on like the tile in my classroom, or like the carpet maybe that would be on there. So what I'm actually referring to in this one, friction force, right? You're pushing against something that's sort of fighting you back. It'd be really easy to slide on ice, hard to slide on carpet. So friction force is typically abbreviated as Fg. If you want me to write that up there, I can. But contact force, Fg. So we've got not Fg. Fg is gravity. Thanks, guys. Fg is friction force, right? It's a resisting force. How about this guy? Our friend here in the, oops, I got to stop doing that. Our friend here in the parachute. He is working against, dun, dun, dun. Well, he's working against the air, right? So with this one, what we've got is air resistance, believe it or not, which is actually a type of friction that's in the same range. You're literally pulling yourself through a fluid. You can talk about that sort of thing. That's a type of a frictional force. He's got weight that is pulling him down towards Earth, but the parachute is providing an upward sort of a force, almost like a buoyant force, I guess, but it's actually functioning on air resistance. So that would just be basically an FF type of a force as well. So I'll put that guy over here. All right, our friend Newton. Bonk, right? In terms of him getting hit on the head with the apple, that is the classic example of Fg. That is our classic field force of gravity due to weight, some object that's literally falling. And again, the apple itself does not have to be in contact with the earth in order to experience that. The further away you are from earth, the less the gravity affects it. But again, that is a field force, so weight. All the stuff on the left, for the most part, is contact forces. All right, how about this one? We've got a magnet here. And a magnet is exerting a pull, or it could be exerting a push, right? An oppositional force against those paper clips. So if it's attracting those paper clips, it's exerting a force. What kind of force is that? Is it a contact force or a field force? Well, does it have to be touching the magnets or touching the paper clips? No. Believe it or not, magnetic force goes over on this case as well. So magnetic force is another example of one of our field forces. And we usually write that F of M for magnetic force. How about this one down here? Electrical force. Does it require contact or not? If you've ever been static shocked as you walked up to something, you know for a fact that it does not require contact. Same thing with lightning, right? The electrical force, F of E for electrical, is actually considered to be a field force as well. So that goes on this side as well. We've got an electric force. This one I'm going to put up here in just a second. The book I'm going to leave it to last because it's kind of a confusing one. And here we've got another case right here where we've got a bunch of guys pulling on a rope. That is a tension force, FT. And tension is a contact force, right? You have to be touching the rope. If you let go, all of a sudden everyone falls down. You have a bit of an issue. So contact force in that case, FT. There is tension in the rope. There's also an applied force, right? They're pulling against something, but the rope itself being tight has a tension force. And I think I mentioned that in relation to the spring as well. Now, this one is definitely one of the weirdest ones. And you're like, it's a book. There's nothing really weird about this. So I would like you to think about the book has weight. Right? And the book is pushing down upon the table. Now, here's the weirdest thought. The table's also pushing up on the book. And that's actually what I wanted to refer to with this picture. So this is kind of a weird one. I'm going to label this because it has kind of an unusual name to it that students don't really realize. So there is, coming downwards from this thing, FG, right? The weight of the book. But the table is also pushing up on the book as well. And so that's kind of a weird thought. Again, book pushing down on table also pushing up on book. This upward force, which in some places is called the reaction force, it's a British name for it. In the United States, it's actually abbreviated as FN. It is called the normal force. Just like you think, not abnormal, it's the normal force. It's the upward force of objects, on objects, I guess, fighting against the force of gravity. And I'll talk a little bit this more later on. So FN, normal force, the forces of things on surfaces. We'll get into more of it in a minute. I just wanted to point out what it was. Okay, so as we're trying to represent these, and I started to kind of draw one in that last picture, as we're starting to kind of represent forces, we start to draw these diagrams, and these are called free body diagrams is a really common name for these things. Kind of like motion diagrams, but something doesn't have to be moving, so that's kind of why we call them a free body diagram as well. It's a simplified model of the things that are present, and we're trying to label our forces that are present inside there. Usually, again, force being a push or a pull, it's got both magnitude and direction, so forces are vectors, right? There's how hard you push, and then there's what direction you're pushing or pulling. And then we can kind of use semi-particle models as well. We don't have to draw fancy pictures. This is a free body diagram like this is a little bit more detail, but I could have just as easily drawn it, as, there's a book, kind of like I did the last one, where there's the FG. They use W here. I don't like this. I think it should be FG is typically how we do it in the United States. So FG is that downward force due to weight. Again, here's that British version of it, reaction force. Again, we don't really use that particular arrangement. We would say there's an upward force of it, which is FN. Again, the normal force. We would have some sort of a surface that it's sitting on, right? There it is. There's our surface right there. And then we'd have the push force. If we're talking about pushing on something, you could kind of draw it this way if you want to. We would call it FA. There's our applied force. And then we have the resistance force, which is the friction force. And the resistance force, if it's moving, again, if it's moving this direction, you'll see me a lot of times draw movement with a squiggly arrow saying, hey, like it's going that way. Then our resistance force would be this way with F, our friction force that's on there. So this is a typical kind of a particle model. We're starting to show all of these different things that are on there. The one thing I don't like about the way that I drew this particular model on here, this is definitely more of a free body diagram because we don't have all of our arrows sort of emanating from the single point force. So typically we might move these around. I'll show you what this looks like in the next image, where it may be more appropriate to draw them all kind of coming this direction, FF that way, and then FA coming that way. So again, it's one of those little weird things about how we sometimes draw these. So for a free body diagram, that's perfectly fine. It kind of shows the directions that everything are moving. And then as we get into kind of talking about that concept I mentioned earlier, that forces cause changes in motion a lot of times, or can result in changes in motion. The big idea here is whether they are balanced or not. And the concept that going along with this is the concept of net force. We're going to add our forces together. And when we add forces together, they have to be added tip to tail. You kind of seen this little cartoon picture on here, some examples of some balanced and unbalanced forces. So balanced forces, they're opposite directions and they add up to zero. So in all of these cases, the upward force, the normal force, what they would call, well, it's not really weight should be downwards, and the reaction force, which is the opposite direction, these are actually colored incorrectly, would be interesting, would actually be backwards. I would say that this one, the upwards force would be the normal force and the downward force would be FG. These are equal and opposite almost always. And you can kind of see there's a difference here in the forwards and backwards forces. The kind of like thrust force or the forward applied force of the car on the ground versus the friction force that's fighting the car. So if you talk about this case right here, the red arrow and the blue arrow are equal and opposite to each other. So if I drew these, I'm going to go to my other pen here, this one. If I have my applied force and my friction force, if they are equal and opposite, we would say that my sum of my forces, I don't know if you've seen this in math class, but it's the Greek letter sigma. But the sum of my forces here would be equal to zero, right? Net force would be equal to zero. This would be balanced. And in that particular case, that just means the car's moving constant velocity. We'll get into that more in the next section. In this one, they don't add up to zero. You can see that the forward force is quite a bit bigger. The friction force is a little bit smaller. So our net force here is not equal to zero. Our net force is this way, right? This force is a little bit bigger than this force is. So we would have a net force to the left, unbalanced, and that car would be accelerating to the left. On the right, we have the kind of opposite example where we have a really small forward force, not very much applied force, and a big friction force. That big friction force, we would call that drag a lot of times, or it could be brakes, right? Which it also causes friction. So in this case, our net force here is also not equal to zero. Our net force is going, this direction. And that's what we would be calling slowing down, right? Our net force is to the, right, which would be this direction on this case. So again, when we're taking a look at our different forces and how we draw them, we're going to do a lot of these free body diagrams like this so that you can kind of see how the net forces work, because almost all the time, that's really what we're really keyed in on. Not any individual force, but the net interaction of these different forces. Which pairs are balanced and which pairs are unbalanced that would be causing acceleration or changes in motion. Oop, that was it. So I think we're all done. Have a good one. So again, as we kind of move forward in the next couple of videos, we'll do some more stuff about doing some math with this. We'll do some Newton's laws and how those apply to net force. And then we'll start doing a little bit of more complicated problems as we move through. So I hope you liked it, and I'll see you guys next time.